Hello, welcome to CSC7013, Advanced Math for Computer Scientists. This is Brady Chen. This is Module 6, Set Theory. Set theory is the mathematical theory of well-determined collections called sets of objects that are called members or elements. Now here's the learning objectives for Module 6. Now first we will introduce the concept of sets, and then we'll talk about the relationships between sets, the relations between sets. And we will talk about some of the operations on sets. Now here, let's talk about another operation. Now that operation is going to combine two sets into a new set. Okay, the new set is defined as the pair of the ordered pairs of the original two sets. Okay, let's take a look at this. So suppose we have two sets, A and B. Okay, now we're going to define a new set. Okay, now we know that you can actually create the A union B, A intersection B, and for A, you can define the complement of A. For B, you can define the complement of B if we agree on the universal set, right? But here, we define another set using something called Cartesian product. So that means we're going to create a new set which consists of all the ordered pair A and B. Okay. Now, well, A belongs to A and B belongs to set B. So it's all the ordered pair. Okay. So now we call this A times B, and that's the Cartesian product. So the Cartesian product basically means it's a new set which consists of ordered pairs, and the first element in the ordered pair belongs to A, the second element in the ordered pair belongs to B, and that's the element which belongs to the A times B. So here is an example. So let's say A is a finite set. A equals X and Y. So these A contains two elements. And B is also a finite element. B contains three elements. Okay. Now what is A times B? A times B should actually include all the ordered pairs of AB. So that means that should include, let's take a look at the first element in A. So that should be X3. So that means it's an ordered pair. The first one belongs to A, and the second one belongs to B, right? And then also X, you don't change the value X in the first, set, but you change the value of second set. So X6 and also X9. So these are three elements which basically belongs to A times B. But we're not done yet, right? So we should also include, the other pairs. Now, in the other pairs, the first element is Y. The second element is actually picked from B. So I can just say Y3, Y6, and Y9. So we should actually include all the combinations of the pairs ordered pairs. Okay. So let's see if A is 1, 2, 3, B is 2, 3, 4. Okay. Now, so A is a set of 3 elements, 1, 2, 3. B is a set of 3 elements, 2, 3, 4. What is A times B? It should be an ordered pair, which is which contains the combination for all the elements in A and all the elements in B. So the best way to do this is to, just say define the element using the curly brace. So the first element, we can actually put the first element in A first, okay, and then the first element in B, which is 2. And then we still keep the first element in A, but we change, and we continue to do that. Now, so here's the first element, 1, which pairs with all the elements in B, which we have 3 cases, right? And then we can change the first element to 2 and pair with all 3 elements in B. So 2, 2, 2, 3. So for 2 sets, A and B, we define the Cartesian product of these 2 sets. Okay, so the Cartesian product of these 2 sets is a new set which consists of all ordered pairs. Now, let's take a look at the example. Suppose I have 2 sets, A, which contains 3 elements, and another set B, which contains 2 elements, 3 and 4. So we define the Cartesian product of A and B, which contains all the ordered pair A and B. Now, well, A is in A, B is in B. So we know that the A contains 3 elements, B contains 2 elements. So now the Cartesian product A times B contains all the combinations of the ordered pair. So now we can illustrate using the space. So suppose A is in a one-dimensional space. We call it X. So A is actually in one-dimensional space. So it contains 3 points, 1, 2, 3. And B is in another one-dimensional space. I use a vertical line to represent another one-dimensional space, Y. So many times we call this X-axis and the Y-axis, and this is the original point. So B actually is in Y, so B contains 3 and a 4. So then we have a 1 and a 2, but 1, 2 is not actually in B. Now, for the Cartesian product of A and B, it contains all the ordered pair. The first one is from A, the second one is from B. So then for each element in A, we can pair with an element in B. So that's 1 pair with 3, and then that's 2 pair with 3, right? And a 3 pair with 3, right? And then I can pair 1 with 4, and 2 pair with 4, and 3 pair with 4. Okay. So for Cartesian product A and B of A and B, there are 6 elements. You know, A contains 3, B contains 2. So A times B, the Cartesian product of A and B, contains 2 times 3, which is 6. It's actually all the combinations of, you know, elements from A and the elements from B. So now we can define some kind of relations between the element in A and the element in B. Okay, so because once we set up a relationship for each value of A, in set A, and then we can, if we can find the corresponding value in B, then we can find some kind of relationships between the set A and the set B, and that relationship is used to, you know, to define some kind of charts or graphs. For example, the calendar years may be paired with GDP. So the calendar year could be represent the first set A, and the GPA could be, you know, corresponding to the other set B. So for each calendar year, you can find a corresponding GDP. I'm sorry. Also, you can actually, you know, pair the days with the average temperature. So I can say July 1st. So then you can find the corresponding temperature, which is, you know, 68. July 2nd, 68, 69. July 3rd, 68. July 4th, 71. So for each day, I can pair with the temperature. So that way we can actually, you know, define the relations, okay, between two sets, A and B. So now from math, that relationship can be viewed as something called function. Okay. Now function f can be regarded as relation between each object x in its first set, you know, let's say set A, and we call this first set domain. So that's the term used in math. And the value we call f of x in the second set B, we call this second set a range. So basically we define the relations between domain and the range, and then we call that relationship a function. Now here's how the function is defined. A function f is a relation within a special with a special property. So function, you cannot just randomly define any relation, but there's a property that this property says each x in the first set is related by f to one and only one value y in the second set. Okay, so that means if you have two ordered pairs, x and y and x and z, so then y and z has to be the same element, because for each x you're going to relate to one and only one y. Now what does that mean? So let's say we have these Cartesian product, right? And then now let's find a function, you know, f from domain A to range B. Okay, so let's do this. I change the color for this, the ink color. Okay, so let's say for each value x, okay, in the domain, which is A, okay, for each value x. Okay, so let's say first I choose x equals 1. For the value 1, then f can be defined as a function that the map, is related to 1 and only one y in the range. So 1 can be either mapped to 3 or 4, but not both. Now let's say the function I'm going to define maps 1 to 3. Okay, so that's the one for value 1 in A. Now for value 2 in A, if x equals 2, so I also going to define a unique value in B. So in this case, I pick this value. So then I'm going to say 2 going to map to 4. And again for 3, I need to pick a 1, so I'm going to map 3 to 3. Okay. Now, so for each value, 1, 2, 3, you're going to map to a unique value element in domain, which is in B, right? Now that way I define a function. Okay. So I map here. So these 3 dots basically defines a function. Now I can define another function called g. So for g, I map 1 to 3, but I map 2 to 3, and I map 3 to 4. Okay, that's g. Now let's actually use another color to represent a g. So to see what's the difference between the function f and the function g. So I can use the, let's see, a blue color. Okay, so that's g. So 1 to 3, okay, 2 to 3, and 3 to 4. Okay, so that basically defines the function g, and this defines the function f. Okay. Now let's discuss another example. Okay, in the previous example, we pick A as a finite set and B as a finite set. So, and sometimes this is called a discrete, set. So it only contains a finite number of elements. Now let's take a look at the example of two sets which contains infinite number of elements. Suppose I pick a x defined as the set of all real numbers, and y is the set of all real numbers. Okay, so x and y are basically the same set, and sometimes we use in math R, capital R, to represent a set of all real numbers. Okay, if I use the curly bracket, represent this. Now, the Cartesian product of x and y can be defined as two-dimensional space, right? So suppose x is a space represent the horizontal line, and y is the vertical one. Now, every point on the x-axis represent an element in x, because x represents all the real number. For example, if I say 1 actually is an element of x, right? And this also one, it's an element of y because it's in y-axis. Okay, now every point in the two-dimensional space represent the element in the Cartesian product of x and y. For example, if I have particular value, say this is 1, 2, 3, 4, 5, 6, okay, and the 7. So this is actually 6.5. And then I can pick another value 1, 2, 3, 4, 5, 6, 7, 8, 9. So if I pick a value 6 and 9, then 6.5 and 9, that's an element in the Cartesian of x and y, right? So I use an ordered pair to represent a point in the Cartesian product. Now, let's define a function. So we can define a function as f. So now, for each value of x, each value x in f, okay, let's say I use f of x. So for each value x, okay, I will define the corresponding value in y as x squared. Okay, that defines a function. So this is an ordered pair. So you're basically going to say, okay, so the function can be defined as, an ordered pair x and f of x. Okay, or you can define the function as x and x squared because f of x is x squared, right? So for each value of x in x, there's a corresponding value x squared in y. So that defines a function. Now, I can also draw a diagram on the two-dimensional space. So let's say I pick some values. I pick some values in x and find the corresponding value in y, right? So let's actually switch to a different color so I can draw this, the function. So let's say we can pick a value x and f of x, which is x squared. So if I pick a value x equals 0, now what is f of x? 0 squared is 0, right? If I pick a 1, then it's 1. I pick a 2, then it's 2 squared, which is 4. And I can pick a 3, which is 9. And if I pick a 2.5, I don't know what is the corresponding value. It's somewhere between 4 and 5, right? But it doesn't matter. I just randomly pick some number. -1. So -1 square, which is 1. -2 square, which is 4, right? So -3, it's also going to be 9. So then we can find the ordered pair. -3 versus 9, related to 9, -2 related to 4, -1 related to 1, 0 related to 0, 1 to 1, 2 to 4, and a 3 to 9. So let's see, 0 to 0, 1 to 1. So if I have 1, pick a 1, the y is 1, and 2 to 4, 1, 2, 3, 4, and 3 to 9, 5, 6, 7, 8, 9. Okay, 3 to 9. And also for negative value, -1, -2, -3. This -1 is 1, -2 is 4, -3 is 9. So we find some of the point. We can connect these points that's the diagram for the function f of x equals x squared. Or sometimes we say for each value of x, that's a corresponding value y. So y equals f of x. Now let's see, what is the, the corresponding value in y for 2.5? We don't know that yet, right? We can use calculator, but I also can guess the value because here's a 1, 2, 3. Now it's a 2.5. Now we can basically estimate the value here. It's approximately 2.5. It's approximately 7 point something, right? I don't know. Let's say 7. It's not 7, but it's close to 7. So that's the corresponding ordered pair. So this is actually a function which is defined as a subset in the Cartesian product of x and y. Okay. Now in the previous slides, we defined some kind of relations between two sets, right? Now one of the special relationship is called a function. For example, if we have two sets A, remember that's the example we used, B, which contains two elements, right? So we define a function which contains the ordered pair. Now in this ordered pair, for each value, each element in A, you can find a unique value in B. Each value in A, like a second value, 2, you can find a unique value in B, so which maps to 4, and the value 3 maps to 3. Okay, so that means for each value in A, we define a unique value in B. Now that basically defines something called a function. Now function is basically a subset of the Cartesian product of A and B, right? Now this relationship is not one-to-one relationship. Okay. Now what is one-to-one relationship, or we call it one-to-one correspondence? Now the one-to-one correspondence between sets A and B can be viewed as a pairing of each object in A with one and only one object in B. Okay, so here the first, the element 1 pair with the element 3 in B, right? But is that 3 the one and only one object in B? The answer is no, because we have another element in A, which is 3, also pairs with 3. Okay, so we have two elements in A, 1 and 3, both pair with 3. So that's not one-to-one correspondence. Okay, because on the other hand, one-to-one correspondence says, with the dual property that each object in B has been thereby paired with one and only one object in A. Okay, but now we find out for each object in B, this is not the case, because for example, object in B, 3, that's the object in B. It pairs with 1, in the meantime it pairs with 3. So that F is not one-to-one, right? Now let's take a look at another example. So suppose we have A is a set of 3 elements, X, Z, and a W. And B is a set of 4, 3, and 9, and also 3 elements. Okay, now if we define a relationship like x maps to 4, and the z map to 3, and the w map to 9. Now that mapping is 1-to-1, right? So x maps to 4, which is unique. Z map to 3 is unique. W map to 9 is unique. Because we can do the opposite. Let's say 4 maps to x, that's unique. 3 maps to z, and the 9 maps to w. Okay, so that mapping is 1-to-1. Okay, now another example is, for example, x maps to 4, and the z maps to 9, and w map to 3. That's also 1-to-1, right? However, if I pick an example like x maps to 4, and the z maps to 3, and the w maps to 4 as well. Now that map is not 1-to-1 because x maps to 4 and the w maps to 4. So that means, if we try to map from B to A, so then you can find out one of the element B, 4, maps to both x and the w. So that's not unique. So that's not a 1-to-1. So here we define the relationship called a 1-to-1 correspondence. So now, if you look at the examples in the previous slides, you will probably find out some kind of pattern. So suppose that I have a set, a finite set, let's say A. A is A, B, and C. Okay. And then A contains 3 elements, right? Then I can always find a 1-to-1 correspondence with another set which contains 1, 2, 3. Right? That's pretty easy. I can map A to 1, B to 2, and C to 3, and then I find a correspondence, 1-to-1 correspondence. Okay. So if a set A is a finite set, and then we can always map to the set which contains the natural numbers 1, 2, 3. Now, depend on how many numbers, number of elements in the set. If you have 3 sets, you can map to the set of natural number 1, 2, 3, right? If it contains 4 elements, different elements, you can map to the element 1, 2, 3, 4, right? So now, basically, for a set 1, 2, and 3, now the number 3 is called cardinal. It's called a cardinal number, or sometimes called cardinality. So then also for every finite set, okay, which contains 3 elements, then because we can build a 1-to-1 relationship with 1, 2, 3, the set of 1, 2, 3, then we also say every actually finite set with 3 elements has a cardinality 3. Okay. So let's say I have another set B, which contains like A, B, D, F, G, H. Okay. So B contains 6 elements, and then we can map B to the set 1, 2, 3, 4, 5, 6. So we can easily build a 1-to-1 relationship, right? Now this one has a cardinality 6, so same for the set B. Okay. Now, so basically for the finite set, the number of elements defines the cardinality of these set. Now for an empty set, if we define an empty set which contains nothing, no elements, right? Now we define the cardinality of an empty set 0. So the cardinality for empty set is 0. Okay. So in general, a set A is finite, and its cardinality is n if there exists a pairing of its element with the set 1, 2, 3, 4, all the way to n. If you can pair the element of this set with the element in the set 1 to n, then the cardinality of this set is n. Pretty straightforward, right? So we have seen that for a finite set, the set which contains finite number of elements, then it's pretty straightforward. So we can always, map any finite set to a set of 1, 2, 3, 4 to n. Okay. Now, if you can create a correspondence, one-to-one correspondence between the set, the finite set, to this particular set, sometimes we use the Sn. Okay. Okay. If we can build a one-to-one correspondence between your set and this set of set Sn, then we can say that the cardinality of your set is n, and so it's pretty straightforward. So now we're going to focus on the infinite set. So we're going to discuss the set with infinite number of elements. Now, in order to discuss this, we need to actually create some kind of notation which was initially used by a German mathematician called Georg Cantor. Okay, he actually used the notation called predicate formula. So he defines the set A as, use the curly bracket and put the element x. So A contains the element such that S of A, x, is satisfied. So that means for the set A, x belongs to A if and only if S of x holds. The condition f of x, S of x holds. Now, S of x could be anything, could be some kind of English statement. For example, you can define A as all the element x such that the x is a positive integer such that the x modulo 2 is 0. Now, x modulo 2 equals 0, that means when x divided by 2, the remainder is 0. Or in another word, that means x is a positive integer such that when x divided by 2, the remainder is 0. So that means x is a multiple of 2. Or x is just an even number, right? So you can define another set, okay, which contains all the element x such that x is a positive prime number. So xx can be any descriptive statement. Okay, he used that notation called the predicate formulas. So technically, we can define any set, right? Set A could be all the real numbers. Set B could be all the people who actually live in the United States. So you can define various different sets. But from math perspective, we want to study the property of these sets. So even though the contents are different, the elements are different, but we try to define, some kind of fundamental properties. Okay, so hopefully, once we actually study one set, And then we can also get the conclusion for the other sets. Now, one of the relationship between two sets is called equivalence. Okay, so two sets, A and B, are called equivalent. Okay, two sets are equivalent. Now we use the notation A is equivalent to B. If and only if there exists a third set, there exists another set. Now the members of this third set are ordered pairs such that the first member of each pair is an element of A, and the second is the element of B. So that means we can find a third set. Let's say set C. Okay, so the C contains the ordered pair, and the first element is in A, and the second element is B. Right? It's like the Cartesian product between A and B. Okay, that's the condition 1. Now, and also 2, each member of A occurs as the first member, and each member of B occurs as a second member of exactly one pair. So that means each member in A and each member in B in the pair occurs, okay, exactly just one pair. So that means if you have like a element like 1 in A pair with X in B, and then that pair is unique. So you cannot have X pair with Y. If that's the case, then X and Y must be the same. Okay. Okay. So that's if A and B are finite and A is equivalent to B, then the third set that established that TACT provides a pairing or matching of the element A with those of B. Okay. So that's called the equivalence. Now let's discuss the equivalent sets in more details. Now first look at the finite set. If A is a finite set, B is a finite set, if A is equivalent to B, so that means both A and B has the same cardinality, or both A and B have the same number of elements, right? Now, for infinite sets, now things are a little bit tricky and also very interesting. Let's see. Suppose I have a set called Sn, which is actually the natural numbers. 1, 2, 3, 4, 5, dot, dot, dot. I can just continue. Okay. So we can define these as n such that the n is an integer, a positive integer. Okay. Now let's define another set. Okay. So then we call the E of n. So it's a E of n is 2, 4, 6, 8, 10, da da da. So if we try to summarize, it's actually a set of positive even numbers. Now, if I use the Cantor, predicate formula, I can write this as 2 times n. Well, n is a positive integer. right? So it's a positive, it's an even number, positive even number. So, and it could be 1, could be 2. So you can represent a 2, 4, 6, 8, right? Depend on the value of n. Now we can build a third set, which contains n and the 2 times n, which we can pair n and the 2n. Okay, so well, n is a positive integer. So then, for each value in Sn, we can find a corresponding value in En. So then we can build that mapping, right? So we can establish the equivalence of Sn and En. So Sn and En are equivalent. Now in here we use A and B, but I use Sn and En. Okay, it's the same. Now this is kind of strange, right? Sometimes when people ask, the question like, even though Sn has infinite number of elements, En has infinite number of elements. Now people sometimes ask, do Sn and En have the same number of elements? That question looks like it's kind of stupid because it's an infinite set. How can we say the number of elements? They're infinity, right? But if sometimes when we build the equivalence, then you can say Sn. So if two sets are equivalent, then you can say two sets has pretty much the same number of elements. That sounds reasonable, right? However, if you look at the details, and you're going to find out En is actually a subset of Sn, right? En is a subset of Sn because Sn contains all the positive integer, but En only contains the even positive integer or positive even integer, right? So now, Sn include the En. Also, Sn include all the positive odd numbers, right? Odd integers. So En is subset of Sn. Also, En is also called a proper subset of Sn. So that means every element in En is an element of Sn, but not the opposite. So there is an element in Sn, but not in En. For example, number 3 is in Sn, but number 3 is not in En. So it's called a proper subset. So that means En is completely included in Sn. Okay. So in this case, we call a subset of A, and also it's called the proper subset, okay, of A. But if both sets are infinite sets, then you can find two equivalent sets, and one is a proper subset of the other. Okay, but that's not true for the finite sets. We will see this in next slide. Okay. Now, for finite set, a finite set is non-equivalent to each of its proper subsets. For example, suppose I have a finite set A. In this case, A contains 3, 1, 0, 4, and 2. Okay. Now, then B is 0, 1, 2, right? And C is 0, 1, 2, 3, 4. Now we can say A and C are equivalent, right? You can build a map, right? So another one, so you can map 3 to 0, 1 to 1, 0 to 2, 4 to 3, 2 to 4. You can build this one-to-one correspondence. So you can pretty much map A and C. But you cannot build that relationship because 4 and 2 has nothing to map. You cannot map 4 to 1 because this can actually, force 2 elements in A maps to 1 element in B. So you cannot build that case. Now clearly, B is a proper subset of A, right? B is actually subset of A because all the elements in B also contained in A. And also there's some element in A which is not in B, like a 3. So B is a proper subset of A. But B is not equivalent to A. Now you can see that the cardinality for A is 5, but cardinality for B is 3. So A and C can build a map. So for finite set, if one set contains a smaller number of elements than the other one, then these two sets cannot be equivalent. So they have to contain the same number of elements. Okay. Now this is not true, however, for infinity sets, as illustrated with the set A and B in the early example, or in our example I use Sn or En, right? But En is proper subset of Sn. Okay, I think it's a good time to stop now because we are actually touching one of the most difficult area in math. It's called mathematical analysis. Okay, so this is a very tough area, but if we continue, we're going to be, touching the very difficult area in math. So I think I'm going to stop right here. So that's probably a good time to stop. Okay, thank you.